What the heck?
Tagon.
Excuse me. Well, I never. You are such a... Mean operator is a function that acts on a function to give you the average value of that function over a certain interval. And I have recently been challenged by a frequent viewer of mine on my also recent video saying that I have a Patreon now, which asks me to give a formula for the nth average of a function. So like iterating that operation on it again and again. You could think of it as being sort of like a complete and utter mother function average operator. And I've been tasked to solve this problem, so let's take a look at that. So what we are going to do today is we're going to explore iterating the operator which gives us the arithmetic mean of a function over a certain interval. And so what do we mean by that? So given a function f of x, which is Riemann integrable on the interval from a, where little a is some real number that we're picking, to, that's like a fixed value, and x is a variable that runs over the real number line. Given that function with this property, then we define the arithmetic mean operator, or average function, you can think of it like that, of f of x, or the arithmetic mean transform, I suppose you could think of it as, to be 1 over x minus this fixed value a, little a, times the integral from little a to x of f of t dt. Because what this is saying is we're going to integrate over this function from a to x, and then we're going to divide by the length of the interval that we're integrating over, and that gives the average value of the function over the interval from a to x. And what I'm being tasked with is calculate what is the nth average of f of x, given some function f of x. And this was actually sort of a tricky problem until I remembered one simple principle from multivariable calculus that I just for some reason couldn't get through my head, and then I was able to crack the problem. So how do you iterate this? And by that I mean this is the average of some function f of t, or some function f of x. Now take the average of this function, because this is a different function on x now. So let's consider what might the average of f of x be. We might also write this as a2 of f of x. We have to have the first average of f of x, and that's going to be in the t world, so we're going to have 1 over t minus a times the integral from a to t of f of s ds, and s is just now some dummy variable, and then of course we're taking the second average of this. So right now this is really this, right? I've just changed the variable, so now we're going to have x on the outside, so it's still a function of x. So now we're taking the average of this. We need to take the integral of that whole thing from a to x with respect to t, and then multiply by 1 over x minus a. So the starting point is the same for each average, just to simplify things. And so you can sort of just pick a and it becomes whatever it is. And so this is the second average. And the idea of this is to figure out what's the general formula for the nth average of any particular function. And it's quite a lovely answer, and it has a lot to do with basic repeated integration. So real quick before we continue, we're going to talk about Koshi's formula for repeated integration. Now, Black Pen Red Pen was able to prove this result in one of his videos, so I'm going to forego proving it here, but we're going to expect a result that looks something like this. So it is a true fact that if you take n integrals of a function, like so, so if you've taken n integrals of a function from a to t1 and then a to t2, where all the tk's and the tn's and all that are the variables of integration, this can be telescoped down into one single integral, which is simply 1 over n minus 1 factorial times the integral from a to x of f of t times x minus t to the power of n minus 1 dt. And if you can quite easily generalize this to arbitrary order of integration, because you can simply use the gamma function as an analytic continuation of the factorial function. So you can have, say for example, 1 over gamma of alpha times the integral from little a to x of f of t times x minus t to the power of alpha minus 1 dt. And this is sort of the generalized integral for any order, alpha. And so, because we're sort of doing an iterated integral like this, but with an extra twist to it, it's going to be similar to this, but it's going to be slightly more complicated. And it's a very, very interesting problem to try and solve. So first of all, let's see if we can derive some properties of this operator that we're talking about here. Let's state again the definition. So we have the arithmetic mean of a function f of x is equal to 1 over x minus little a, where little a is the starting point of the integral, and we go from a to x of f of t dt. So that is the definition, right? This is what we mean by this operator, capital A. This could also be written, for example, a being applied to the function f evaluated at x. So what we want to do first is maybe explore what we can find out about it. So the first step might be, let's just try iterating it once. Let's do a squared of f, or a2 of f, whatever you want to call it. So like so, we're doing this. And this is precisely just doing this process twice. So on the outside, right, we have, you know, this, the outermost layer that's just going to by default be x. And then we're going to have one more variable of integration on the inside, still starting at a and going to some variable t. And so there's multiple ways that we can approach this problem. So we've iterated the average once, right? We have the average of the function f and then the average of that average on the outside. And so what we can do first is sort of realize something. If we know the antiderivative of the function f, the thing that if we took the derivative of it, we would get little f back, then we can actually say that this is equal to the antiderivative of f at t minus the antiderivative of f at a. Which is actually a nice little simplification, because that means that this is precisely, in the context of x, this is precisely the antiderivative of x minus the antiderivative, the antiderivative of f at x minus the antiderivative of f at a divided by x minus a, which is precisely the average rate of change between a and x of the antiderivative of f, which if you took the limit as x approached a, you would actually get f of a, because this is just the difference quotient, like the derivative, but without the limit. So once you take the limit as x approaches a, you get the derivative of this function at a, but the derivative of the antiderivative of f is just f, so you get f of a. Not really necessary to know about the rest of this problem. That's why I didn't write it down, but it's neat to cover anyway. This whole thing now is literally just going to be equal to this. And so we're just going to put this under the integral, and it's actually going to make it pretty easy to approach in a certain way. So we now have that this is equal to 1 over x minus a times the integral from a to x of the antiderivative of f at t minus the antiderivative of f at little a divided by t minus a dt. And now the key is going to be to do integration by parts on this to see what we can get out of it. So we're going to take the derivative of the numerator, and taking the derivative of the antiderivative of f at t just gives us f of t dt, because of course big F of little a is a constant, so it goes away. And then we're going to integrate 1 over t minus a dt, which gives the natural logarithm of the absolute value of t minus a. When we do integration by parts, we multiply these functions together, and then we evaluate them at x, and then subtract the evaluation at a, at least whatever the bounds of integration are. So let's see what would happen when we do that. So we plug in x, we get big F of x minus big F of little a times natural logarithm of x minus a. Well, that's fine, but then once we plug in a, we're going to have natural logarithm of 0, and that's a problem. But we're just going to assume, for the sake of the elegant math, that big F of t is a function that goes to 0 faster than natural logarithm goes to negative infinity, and so it will go to 0 if we plug in a, because we have big F of little a minus big F of little a, which is 0, and so that part doesn't matter. So plugging in a doesn't matter, so we just need to take what we get when we plug in x, so we get big F of x minus big F of little a times the logarithm of the absolute value of t minus a, and remember we're still dividing by x minus a. And then we're going to have the minus the integral of the product of these two functions, so minus the integral from a to x of f of t times the logarithm of the absolute value of t minus a dt. And you'll notice we have right here the average of f, right? So this right here is the average of f. So we can actually just replace this with the average of f of x. And notice, oh, sorry, I forgot to multiply the x minus a in here as well, because we have 1 over x minus a there. That makes this the average of f times the logarithm of this function right here, which is also this function here. So we can rewrite this as an average, right? Because it's an integral from a to x of some function of t divided by the length of the interval. So that's the average operator on this function here. So we're going to have minus the average of f of x times the logarithm of the absolute value of x minus a. And that is what the second average of a function f of x is equal to. And what we're going to do is we're going to manipulate this a little bit more, but this is a neat little result. So you can get that sort of on the second one. The rest of them we sort of need to find the general pattern. This is sort of just a nice result. So what we're going to do now is we're actually going to write them in their integral form because we have an average here and an average here, which means they're both integrals like this one is. So what we're going to do is we're going to rewrite these like this. So this is going to be, this has to be equal to 1 over x minus little a times the integral from little a to x of f of x. Sorry, that should have been an x right there. My mistake. I should have put an x there. That was confusing me. So what we're going to end up with when we write this average and this average as their integral forms, we're going to get the logarithm of the absolute value of x minus a divided by x minus a, because that's part of the definition of the average, right? Times the average of, well, so that's part of the average of f of x. So we have now the integral from little a to x of f of t dt. And then this is minus 1 over x minus a, because we're doing an average, times the integral from a to x of f of t, times the logarithm of the absolute value of t minus a dt. Just using the definition of what the mean operator is for, or what the definition is. What we can do is, because these have a factor of 1 over x minus a, and the integrals go from a to x, we can just put this inside this integral, bring them together, and we end up with this. So we end up with 1 over x minus a times the integral from a to x. I have a factor of f of t in both of these as well that I can factor out, so I'm going to get f of t times the quantity ln of the absolute value of x minus a minus ln of the absolute value of t minus a. So I'm going to get f of t times ln of absolute value of x minus a minus ln of the absolute value of t minus a dt. Now, I can combine these using log rules, and I'm going to get log of this divided by this, but the absolute value of something divided by the absolute value of something is just the absolute value of the quotient of the two things, so this is the same thing as 1 over x minus a times the integral from a to x of f of t times the natural logarithm of the absolute value of x minus a divided by t minus a dt. And so that is a single integral version of the second average of a function t. And it looks almost the same as the regular one, the first average, except now there's this factor of the natural logarithm of something in there. And it's actually going to be possible to put every single iteration in a single integral form, and that's going to be the final formula for the video, which is quite neat. And so this is the second iteration of the average of a function f of x. So I'm going to just say what the third iteration is, and then I'm going to demonstrate what the general pattern is using proof by induction. So we've done 3 averages now, right? And so I'm going to say what this is now. So this is precisely equal to 1 over 2 times the quantity x minus a times the integral from a to x of f of t times the natural logarithm of the absolute value of x minus a over t minus a to the power of 2 dt. Now, this is quite similar to the one that we just saw, and in fact, if we take n iterations of the average of some function f of x, then we will get precisely 1 over the quantity x minus a, where little a is again the starting point of the average, times the quantity n minus 1 factorial, times the integral from little a to x of f of t, times the natural logarithm of the absolute value of x minus a divided by t minus a to the power of n minus 1 dt. So this single integral form is the final result of doing iterations of the average of a function. And so if you want to take the average of the average of the average of the average, you just have to plug in 4 wherever you see n, evaluate that integral, and your answer will be that function, were you to start at whatever number the letter little a represents. So let's prove this. So the base case has already been demonstrated. It's a little cheeky to use the first case because that's a definition, and so we've already proven the second case because the second case was quite easy. Oh, I'm sorry, this should have been 3, by the way, because I changed this to 3. So what we should do is try to make sure that our 2 cases that we know about actually fit the bill. We can't actually plug in doing no averages into this because that would require plugging in 0 here, and then we'd have -1 factorial. So we can't go back to just f of x. So it would seem that an inverse averages might not be possible. We might have to consider, that would be something we'd have to consider. So let's plug in 1, right? We've taken 1 average. So we plug in 1 here, we get 0 factorial, that's 1. We plug in 1 here, we get 0, and this whole natural logarithm is raised to the power of 0, so that goes away. And that leaves us exactly with the definition of what we said the average operator was, because we have a 0 factorial down here, because that's 1, and we have that whole natural logarithm thing to the power of 0, which is also 1. But again, that's the definition, so it seems like cheating. But if we do the second average of f of x, then this gives us 1 over x minus a, technically times 1 factorial, times the integral from a to x of f of t, times the natural logarithm of the absolute value of x minus a over t minus a, to the power of 2 minus 1, which is 1. dt. So it does fit the pattern, and so this will be our base case, and it was already proven because I demonstrated it by not that one, but I demonstrated it by evaluating it on the previous board. So we're going to assume that n equals k is true, and then prove or show that this implies that n equals k plus 1 is true as well. So so we've shown that it works for the base case. We're going to assume that it works for some case, and then prove that that implies that the next case works as well. Then we can just say, okay, that some case that we started with is just the first case, and then that implies the second, which implies the third, which implies the fourth. And so it's a domino effect, right? It's just proof by induction. So we assume that the kth case is true. So we're going to plug in k for n, and then prove that k plus 2 works. So that's what we're going to do. And then once we've done that, that proves the theorem, which is what we are trying to do here, right? So we are assuming that the kth average of a function f of x is precisely 1 over the quantity x minus a times k minus 1 factorial times the integral from a to x times f of t times the natural logarithm of the absolute value of x minus a over t minus a to the power of k minus 1 dt. So that is the full-on integral. It's quite a mouthful, and so we're going to now prove that the k plus first average is just this with k plus 1 plugged into it. So let's take the average of the kth average of f of x and see what it gets us. So we're taking the average of the we're taking the average of the kth average of f of x, which will precisely be the k plus first average of f of x by definition, and this is going to be 1 over x minus a times the integral from a to x of 1 over t minus a times n minus 1 factorial times the integral from a to x of f of t times the natural logarithm of the absolute value of x minus a over t minus a to the power of k minus 1 dt. Sorry, this should have been a t, and this should have been an s, and this should have been a t, and this should have been an s, because we're going like one level deeper, right? So all of the things have sort of changed places. What was once x on the outside is now t under an integral, and we have a new x variable on the outside. And remember, this was our assumption that this is precisely equal to the kth average of f of x. That's the induction hypothesis. And now we're going to morph this into this with just k plus 1 plugged into it, which will prove the theorem. And I will have completed the challenge. So let's see what we can do. As it turns out, the challenger of mine said that he used integration by parts to figure this out. I actually discovered or found how to do it by actually using the fact from multivariable calculus that you can just exchange the integral by doing a special swapping of the bounds. And that actually got this solved, because what I want to try and do is get the function f of x that we've picked out of that integral and into the outer integral. So what we're going to do is move everything inside of here, except the x minus a and the n minus 1 factorial. So the n minus 1 factorial is going to get pulled out, so we're going to get 1 over x minus a times n minus 1 factorial times the integral from a to x, and we're going to bring the 1 over t minus a into the integral, times the integral from a to t of the integral from a to x of the integral from a to t of f of s divided by t minus a, times the natural logarithm of the absolute value of t minus a divided by s minus a to the power of k minus 1 ds dt. And so now what we're going to do is we're going to exchange these bounds, we're going to exchange the order of integration, and so we're going to have to move the bounds around. So what we need to realize is that we are moving about in the s and t axes. So you can think of this as the s axis and the t axis, and notice that we're starting with the integrating over s, and we're going from some number a to the function t. So it's like y equals x if we were integrating over x and y. In this case, it's s equals t. So it's just going to be this linear function here that looks like y equals x. And so we're integrating from here up to that function there. And so now we've determined the bounds that we have in the s world. Let's determine the bounds that we have in the t world. So we're going from a to x, but of course x is not our variables here. X is just a constant with respect to these two variables of integration. So we're going from a, which is going to intersect right there on the t-axis again, and then we're going to go to x, right? X is a constant with respect to t. So we go out to some x right there, and because we're integrating from a to t, in the s world, that's like we're going from here to there, right? We're going from there to there. And then in the t world, we're going from there to there. And so we're integrating over this triangle in the plane. That's essentially what we're doing with this integral here. And so we want to exchange the bounds of integration so that we integrate with respect to t first, and then with respect to s, so that I can factor out the f of s, as it will be a constant with respect to t. And so here's how we're going to do that. We first need to see what we would need to call it if we were going to go from over t first before we did s, as opposed to doing s first like we're doing now. So we need to think, okay, I'm going from this function with respect as a function of t, as a function of s. We're now looking at sort of this way, from here to here. So we're actually going from s to x if we consider our integration over t first. So our first integral will be from x to s of all the same stuff on the inside. So f of s over t minus a times the natural logarithm of the absolute value of t minus a over s minus a to the power of k minus 1 dt. All right? And now we're going to integrate over s on the outside of that, and we're going from a to x, right? Because we've already set up this slanted bound by going over by integrating over t. Now we're integrating over s, and we're going to be bounded by that anyway, so we can just go from a to x. This has to be x as well in the s world, because this is the function s equals t, so the s coordinate and the t coordinate must be the same. So this integral will just go from a to x. No, I'm sorry, this should have been from s to x, my mistake, because we're going from t equals s to x, and then in the s world we're going from a to x, like so. So those are the exchanged bounds of integration. I hope that wasn't too confusing. It's a little iffy to try and draw something and then explain how you're exchanging the bounds, but if you know how to do that from multivariable calculus, then you're probably fine. But now what's good about this is we can factor out the f of s, because now we're integrating with respect to t first, so it's a constant right now, and so we can just factor that out entirely. But now we can evaluate this integral quite simply. So what we're going to do is we're going to let u equal the natural logarithm of t minus a over s minus a, which means du is equal to 1 over that thing on the inside, so s minus a divided by t minus a, times the derivative of that thing on the inside. But this is with respect to t, so we're just going to get 1 over s minus a. So times 1 over s minus a, and those will cancel, and we'll just get 1 over t minus a dt, which is precisely what we have anyway, right? So doing this as our u and then this as our du really simplifies the integral. So now we have the integral from a to x of f of s times the integral. So now we have to be careful. If we plug in s here, you'll notice that we get s minus a over s minus a. That's going to be the logarithm of 1, which will be 0. So we will have 0 in the bottom bound there. And then if we plug in x, we're just going to end up with log of the absolute value of x minus a over s minus a, and that's the upper bound of our integral. So that's kind of funny because it's very clunky, but that's the upper bound. And so now we have u to the power of k minus 1 du. So u to the power of k minus 1 du ds, right? And now this integral is really easy because this is just the power rule, right? So we just have u to the k minus 1. That's just going to be u to the k over k. And we can't forget this stuff on the outside, right? This is all going along for the ride. So this is still there as well. So we have 1 over x minus a times n minus 1 factorial. And that's being multiplied on here as well, like so. And integrating this gives us, this right here is going to be u to the k over k, evaluated from 0 to the logarithm of the absolute value of x minus a over s minus a. Plugging in 0 will give us 0, so that one doesn't matter. And plugging this in will give us this to the power of k, and then this k, sorry, this should have been a k the whole time. My bad, because we're doing the kth version, right? So that should have been k, and so should this have been k. Sorry, my mistake. All of these should have been k. I apologize for that. Those all should have been k. That's very unfortunate, but I hope it's clear what I meant, right? I'm starting with the kth case right there, so those all should have been k, not n. We assumed that n was good at k. We're proving that it's good at k plus 1. And so this k can be factored out of the integral and go here to make this k factorial. So this k goes right to there, makes that k factorial, and then plugging this into there, we end up with 1 over x minus a times k factorial times the integral from a to x of, now we can just make st again because it doesn't really matter what letter we use, it's a dummy variable anyway. So f of t times this to the power of k, so log of the absolute value of x minus a over t minus a to the power of k dt, which is precisely what was to be proved, right? So QED, thus it is proved. So what we did was we showed that the kth iteration of the average operator on some function is equal to this expression right here by first demonstrating the base case, the first one that really counted, which was 2 iterations, and then we assumed that it worked for some number k, and then we proved that it was true for k plus 1. Based on that assumption, which tells us that, of course, it is true in general. So let's take a look at this a little bit because it's very interesting. So what this is saying, let's just write it out. So what has been proven? We've shown that if we take n averages over some function, f of x, we will get 1 over x minus a times n minus 1 factorial times the integral from a to x of f of t times the logarithm of the absolute value of x minus a over t minus a to the power of n minus 1 dt. This is the formula for repeated averaging. Sure, you could call this, you could maybe think of, ooh, you know what might be a good way of doing this? Or what might be a cool way of using this? Sometimes integrals that are improper don't converge, just like some infinite sums. So perhaps this could be like a continuous version of Cesaro summation, like the one that Mythology did in his video. That would be pretty neat if this was like some continuous version of Cesaro summation. You know, finding an improper integral that doesn't converge, but maybe doing the average function a couple of times does make it converge, and that can be the definition of the value of that integral, like something that's assigned to it, which I think is pretty neat. That seems like a neat idea. You can also generalize this idea to geometric means using the product calculus stuff that I've shown in a couple of videos and that Dr. Payam did as well, and it simply is this expression here. So it's a little bit more complicated, but the only difference is that it's e raised to that whole expression, and instead of just f of t, it's the log of f of t. Unfortunately, logs and logs can't be combined very nicely, but you know, such is life. So there's a couple of neat examples of, and I'm not going to really delve into this, but it's something one might want to explore. So let's talk about a couple neat examples of this stuff right here. What if we take the nth average? In fact, we can actually get a neat little expression by doing integration by parts once to result in this expression as well. I tried doing integration by parts once more after this, but it didn't seem to work out nicely, so it seems like this is the way to go if you're going to do it once at all, it comes out to this. So I did integration by parts once, the power goes down by 1, the factorial goes down by 1, and then you get this factor of t minus a in the denominator there. And you can do, if you do integration by parts once, you end up with this expression here. I'm sorry, this should have been the antiderivative of f, if you know the antiderivative. So that's a neat little expression as well. And to go again doesn't really work very well, but if you plug in, say, n equals 2, you get the second iteration of the average function, which is quite nice. And my challenger was quite right, because this does look a lot like Cauchy's formula for repeated integration, because remember that was just, integrating n times over some function f of x was precisely 1 over n minus 1 factorial times the integral from a to x of f of t times x minus t to the power of n minus 1 dt. And so they're very similar, right? So this is repeated averaging, this is repeated integration. So they're quite close to each other, and it's very neat that there's this sort of logarithm exchange that happens there. You can also quite easily extend this idea to arbitrary degrees of integration or averaging by simply plugging in some real number alpha, because you can use the analytic continuation of the factorial function, which is the gamma function, right? So we can get arbitrary averaging, so some index alpha. I don't know if there's any restrictions on those values. I haven't really explored it very much, but we'll get x minus a times gamma of alpha times the integral from a to x of f of t times log of the absolute value of x minus a over t minus a to the power of alpha minus 1 dt. And so that gives you arbitrary averages, which is quite nice. And if I'm not mistaken, if you let n go to infinity and you take like the infinitieth average, right here, if you take like the infinitieth average, it tends towards f of a, I believe. I believe that's what it does, f of little a, which is all quite neat. It's not too hard to see that this would be a linear operator, because if there was any constant times the function, it could simply be factored out. And if it was a sum of two functions, you could just distribute this logarithm onto those and then separate the integrals out. And so this is definitely a linear operator, which has some nice properties, which gives some nice properties for it. But if I'm not mistaken, this is the correct answer, so I believe I have won the challenge, Mr. You-know-who. And just to be sure, I do have two patrons now on Patreon. One is a pentagon supporter and one is a decagon supporter. They have asked me to remain anonymous, so feel free to ask me if you would like to not be mentioned by name at the end of the video. If you do not, then I will assume that you're fine with it, so please express that desire if you choose to support me on Patreon and would like not to be mentioned by name. So, wonderful, thank you so much for watching. I hope this wasn't too confusing, but it was a fun little problem to solve, and so I believe this is the final answer. It would be interesting to know what the inverse function might be, you know? I'd have to explore that a little further, but for now, this is where I'll stop. Thank you for watching.